Now let's discuss the solutions of activity number 7. The first half is section 3.3, so we want to find a calculation between two complex numbers, 1 minus I minus 2I plus 3. So essentially, you are going to separate the complex part and the imaginary part, but making sure that each piece is properly grouped. So those two are the real part, those two are the imaginary part, so you can get your function together pretty easily by grouping them. So it's 1 minus 3, and also it is a negative I minus 2I, so you end up with 2 minus 3I, which is your final answer. The next problem is, by the way, the bar means conjugate, and the order of calculation is identical to what you've learned before in algebra. So this problem says I want twice of the 2I plus 3 and then find the conjugate and then add to my other complex number, which is 1 minus I. Multiplication is trivial. You distribute the 2 to FOIL things out, so you have 4I plus 6, and then you plus 1 minus I. Well, to find the conjugate, it's always about flip the sign of the complex part, so you end up with negative 4I plus 6 plus 1 minus I. You will realize those two are the real part, those two are the imaginary part, so you're going to group them separately, so you end up with those two gives you 7, those two pieces gives you minus 5I, so that's supposed to be your final answer. The next part is also very interesting. You have 1 minus I multiplied by 2I plus 3. So if you were to FOIL things out one part at a time, it's 1 times 2I, add to 1 times 3, add to negative I times 2I, add to negative 1 times 3, to end up with 2I plus 3 minus 2I squared minus 3, where you have two real part, where you have, negative I times 3, my bad. This is negative I, therefore minus 3I. So what you end up with is going to be two imaginary part. This piece, I squared is negative 1, so technically it's negative 2 times negative 1, which is positive 2. So your real part is 3 plus 2, your imaginary part is 2I, and the negative 3I. So you end up with 5 minus I. This is your solution for the multiplication part. So one extra note, which I want to repeat for everyone, I squared is negative 1. The next problem we want to we have 3 as a 0 for my polynomial. I want to find the complete factorization. So essentially, you want to find all other zeros of your function. Well, in order to find all other ones, you need to know the quotient first. So basically, the first thing is f of x is going to be equivalent to x minus 3. You have x minus 3 as a factor because 3 is a 0 of your function, times something else. This something else should be a quadratic function because the order should match. This is order 1. This must be of order 2, so you can achieve order 3. So once you find a quadratic function, then we should be able to find a factor of the quadratic function. So in other words, if you want to find this, you need to have f of x divided by x minus 3. So to do synthetic division, you have 1, negative 3, 4, negative 12. You divide by x minus 3, so you put 3 here. So you end up with 1. 1 times 3 is 3, add together 0, 3 times 0 is 0, 4 plus 0 is 4, and then those two gives you that. Therefore, your quotient, the function you are supposed to put here, is going to be x squared plus 0 times x plus 4, in other words, x squared plus 4. The question now is how am I supposed to factor my function which goes from which is x squared plus 4. Well, if you can't factor it right away, your other idea is to find the zeros of this function, which leads to quadratic formulation. So you have negative b plus minus b squared minus 4ac over 2 times a. So it's negative 0, which is nothing, plus minus negative 16 over 2, which is negative 1, and negative 16 put together. So you end up with plus minus square root of negative 1 is I, square root of 14 is 4, 16 is 4, so you end up with plus minus 4I over 2, which is plus minus of 2I. So you find your two other zeros of your function, therefore you can factor the whole thing as, as f of x being x minus 3, x minus 2I, and x minus negative 2I. don't forget you are always supposed to have x minus the expressions that makes your function to be 0. Okay, so if we continue our discussion to next problem, it's essentially the same thing. One of the zeros given to you, you have your function f of x, and then you can try to split them into different structures. So it's essentially the same thing. You have one function, you have one factor, you want to find the rest part. The only special thing is if you have 1/2 of I, then you must have negative 1/2 of I, because those numbers always appear in pairs. So you have different ways to find the last factor left. So one way we can do it is to do synthetic division. So you have 12. Okay, don't forget you are supposed to have x minus 1/2 I, x minus negative 1/2 I. The question is, what's the term left? So you need to have your function f divided by this term first, divided by that term, and then what's left is going to be of order 1. So let's do our division. Well, I can do synthetic division with with imaginary expression as well if we wanted to. So this is 12. 12 plus 1/2 I is 6i, so we have 8 plus 6i. If we multiply 1/2 I to it, it is 1/2 I is 4i. 1/2 times 6 is 3. I squared is 3, so that's that. And add together is 4i. 4i times 1/2 I is negative 2. They add up to 0. So keep in mind, if you have something as a factor, your remainder should always be 0. So this is something that actually makes sense. Therefore, the quotient or the multiplication of the two other factors is supposed to what you have here. So I can keep doing my calculation. If I know the multiplication of two terms, I want to find one of the factor, then I only need to divide by the other factor. So I have 12 here, multiplied together, it's negative 6i, it's 8. It's negative 4i, add up to 0. So my quotient, according to the structure, is going to put there, which is 12x plus 8, which gives me my final answer. Okay, so keep going with my discussion. Construct a polynomial function of degree 5. The graph will look like that. So first of all, you realize your end behavior goes like that, which means you have negative of x to the odd power, which makes sense because it's already said that you should have a power of 5. So that's the first thing I have. And then what are my zeros? My zeros, according to the graph, it happens at 1, it happens at negative 1, it happens at the point of negative 2. And as a matter of fact, all three different points, you will realize that your function actually would go across x-axis. So those are the three zeros. So your function would be having x minus negative 2, x minus negative 1, and x minus 1. But of course, they cannot all be of order 1, otherwise it won't add up to 5. Well, you could have proposed any one to be of order 3 and the other two to be of order 1. Currently, I'm going to propose this one of order 3 because conceptually, the one that's flat should have a larger degree, which we didn't discuss in more details. So you could have chosen 3 here and 1, 1. You could have chosen 1, 1, and 3 here. They all work. But that's not finished yet. You all go through x-axis, which means you go through 0, 2. So your function is supposed to look like that. Therefore, when my input is 0, my output is 2. So I have n, I have 0 minus negative 2, which is plus 2, 0 minus negative 1, which is plus 1, 0 minus 1, 3. So 2 is a times 2 times negative 1. So I end up with a being negative 1, which agrees with my assumption that's supposed to be something that's negative. Okay, I'm simply saying this is negative. I'm not saying it's literally negative 1. It could be negative 5, something like that. We verified our calculation that should be negative 1. So my final conclusion tells me my answer should be negative x plus 2 multiplied by x plus 1 multiplied by x minus 1 cubed, which is my final answer for this problem here. So the next part, we want to construct a polynomial function given the degree of 6, and there are two zeros happened at 5i of multiplicity 2. Okay, so my zeros are 5i and something else, because you know they appear in pairs, and then 2 minus 3i, and again something else because you know complex numbers appear in pairs. So you would have multiplicity, well, this is multiplicity 1, so the other one is multiplicity 1. If you have 5i, the other one must be multiplicity 2, they must match. So the conjugate number of 5i is negative 5i. The conjugate of 2 minus 3i is 2 plus 3i. If you do a quick check, 2, 2, 1, 1, they do add up to degree 6. So we have a function figured out. Well, because it didn't tell us any other information, so there's no requirement about how you choose your a, but the rest part is kind of fixed. X minus negative 5i squared, x minus 2 minus 3i, and x minus 2 plus 3i. You could have simplified it. You could say it's any arbitrary number, but it's not 0 for sure. And then x minus 5i squared, x plus 5i squared, x minus 2 plus 3i, x minus 2 minus 3i. Or you could simplify it even further if you want it. So we said if you have a pair of conjugate number multiplied together, it's very easy to conduct calculation. It's a real part squared plus imaginary part squared, and it's of order 2, so it's squared. Similarly, this is a real part squared plus imaginary part squared, and of course, there's no order 2 because both of them are of order 1. Okay, it's order 1 here. So this is what we end up with, and of course you could have stopped here, or stopped here, wherever you wanted to stop. As long as you give me the basic structure, you get full credit. So the next problem, I want you to find the vertical and horizontal asymptote of my function, also find x and y axis of my function. So to find the vertical asymptote, the idea is to set the denominator to be 0, and the numerator should not be 0. Therefore, you end up with x being 2 or negative 2, but you're also making sure x is not 0, which is perfectly fine. So your vertical asymptote is x being 2 and x being negative 2. Make sure you write your answers such that they all look like lines. Horizontal asymptote is a discussion of the leading terms, which is x over x squared, which is equivalent to 1 over x, whose end behavior is going to look like y equals 0 because the denominator is dominating the function behavior. So you have 1 divided by large numbers, which is pretty much 0. To find x-intercept is essentially when would my function value be 0. So you have f of x being 0, in other words, x over x squared minus 4 is 0. It tells you your numerator should be 0 and your denominator should not be 0. Put two parts together, you end up with x being 0, which is your x-intercept. To find your y-intercept, what you end up with is the function with 0 input. So you have 0 divided by 0 squared minus 4, which is 0, over negative 4, which is 0. So your y-intercept is also 0. So we're going to reinforce our understanding by identifying horizontal and vertical asymptote repeatedly for the next two questions. So again, horizontal asymptote is about the discussion of the leading term for both numerator and denominator. In this case, it's simplified into 2, so my final conclusion is my horizontal asymptote is 2. Again, it's about discussion of the leading term of your function, which is x squared on the top, which is x on the bottom. So the discussion of the leading term is equivalent to of the horizontal asymptote is a discussion of the end behavior of function x, which is a tilted line. It would never behave like a horizontal line, so it does not exist. The horizontal line doesn't exist for this function. If we were looking for the vertical asymptote, again, it's where the function is not defined. So my denominator is 0 and my numerator is not supposed to be 0. So putting two parts together, the first one says you shouldn't choose x being 0. The second one says you should choose x being 2 or negative 2. So my final conclusion, my vertical asymptote is x being 2 or x being negative 2. I have two vertical asymptote. Well, just to clarify, for any arbitrary function, you may have at most two horizontal asymptote. You may have none, you may have one. For vertical asymptote, you could have as many as possible based on the structure of the function. Okay, so let's keep going. My vertical asymptote for this particular structure, I want my denominator to be exactly 0, but my numerator should not be 0. So it tells you x is negative 2, but it shouldn't be 0, it shouldn't be 2, which is totally fine. So my final answer in this case, I have one vertical asymptote, which is x is negative 2. To identify the whole of a rational function, it looks very similar to the identification of vertical asymptote. They both happened at a place where your function does not exist, hence your denominator should be 0, just like vertical asymptote identification, but you want to make sure your numerator is also 0 simultaneously, so there's some kind of cancellation, so you won't have to deal with the case where your function behaves like infinity. Well, the first problem is quite straightforward. It means x is 1. The second one means x is 1 and negative 1. So to combine two conditions together, the only possibility is you have x being 1. So your whole technically is 1 with some y component to be identified. For simplicity purpose, I could have only specified the first part. Okay, the second piece is I can realize x is not negative 2, but you may realize the first piece is quite hard to solve because it's a cubic function. So my option, since I need both equations to be true, by having the second equation only getting one answer, you realize that no matter how many answers you have in the first one, your final answer could be at most 1, which is this negative 2. So what you could have tried is you could have tried to plug negative 2 into your first equation, see if that makes sense. So you have negative 2 cubed plus 8 equals negative 8 plus 8, which is exactly 0. So you realize this one only have one solution, but by plugging this into your first equation, the first one also makes sense. In other words, x equals negative 2 is also a solution of the first function. So what you're going to get is x equals negative 2 as your final answer. So in other words, if you have two functions, both have to be true, and you want to find the shared answer. If one of them is very hard to solve, the other one is very easy to solve, you just solve the easy one. It tells you the largest possible solutions you could got, and then plug your simpler solutions into the complicated function, see if the other one makes sense. If that makes sense, that's good. This is an acceptable solution because we make both equations to be true. Okay, let's be flexible. Don't always say I need both of them to be true, then I need to solve both of them. Not really. You want to find the shared solution, so find a minimal set and then make sure that makes both of those to be true, and then you are all set.